Hi everyone, this is a video to an introduction to extreme value theorem, and there will be a proof will be also available after this video. So extreme value theorem says the following: if a function is continuous on interval a to b in the mathematical sense, the limit value is the same as the function value, then f has a maximum and a minimum. So that means there is a function value and two of the function values, so that all the other function value is trapped in between this value f of c1, f of c2. This one's called maximum and this one's called a minimum. So what I'm going to do here, it's very similar to what I did with the intermediate value theorem. We're going to pretend the only numbers we know is rational numbers, and suppose we haven't discovered the irrational number yet. So you sit down and plot all those rational points in a number line. It seems like if you keep plotting those points, they're just filling in every position in here. So the keyword is the position. So all the position we know, we can understand, is just rational numbers. And we haven't discovered square root of 2 or something like that. So we plot all the positions we know, and it looks just like, continuum. So here, right word to describe what we're doing here is a dense property, but at this stage, because we don't know a whole lot of more numbers, this continuum of this object is mingled together with the dense property of rational numbers. Notice that with this idea, we can still define everything. Suppose we're looking at a function who spits out rational numbers. Of course, that's all the numbers we know. So we can define a limit. So xn, rational numbers approaching c, however you approach it along the rational numbers. If all these corresponding function value approach to a fixed number L, no matter whenever you have this sequence, to a fixed number L, that's the idea of a limit of a sequence. That makes perfect sense. From there, we can define a continuity of this function. Okay? So if the function values is equal to the limit value, and if that's happening everywhere in a given interval, we call it a continuous on interval. So all this thing makes sense. Now from there, I'd like to take a look at this this example, f of x equals x cubed minus x, and consider the interval from -1 to 1, open interval. And if you plug in all the rational numbers, we know -1 to +1. If you plug it in here, they're all rational numbers. So I want you to think about all the continuity we defined there. It makes perfect sense. This function is continuous on that interval. And it seems like to our visibility, that looks like continuum. And even the graph of this one looked like a continuum. So here's a key thing. If you sketch this function using the computer, actually when computer program goes through all this, they actually go through finitely many points. They're all rational numbers. So that the picture you see is really realistic to what we are doing here. So we have this graph, -1 to 1. The graph looks like this. From here, usually that we go intuitively, okay, this looked like a continuous graph, and it seems like there is a highest point right there, and there's a lowest point right there. So that must be called maximum value, and that must be called a minimum value. So that's how the extreme value theorem is usually introduced. If you believe this continuous picture, that we have this highest point and lowest point. It should be, especially this part, there should be a function value in here, rational number, that attains that highest point right there. But the fact is that there are no highest point in this graph. Namely, if you have a point right here, there will be always another point, a rational number you can find. You can find a slightly higher point. This is very puzzling, and that's exactly the point of this demonstration. So if you think that highest point is natural from this looking at the picture, that must be highest point, and actually the fact is not. That you can always find the higher point over there. Now let me convince you, going back to the real numbers. Suppose we discovered more numbers like square root of 5 and square root of 3 and so on. So using those numbers, we throw in more numbers into the real line. Then it turns out they're using those numbers, square root of 3, you can hit that highest point. the rational number is not enough. You have to use the square root of 3 to reach really the highest point. Once you allow the square root of 3 sitting inside in here, then we can attain that number highest point. Everything else you plug it in here will be lower than that. Therefore, we obtained the highest point as a function value. The puzzling part is that, okay, how do we know? So we discovered more numbers, but what if there are out there and even more numbers that from there there's some more stranger examples such that what just happened with a rational number can happen again. So that's the right way to think about it, and that's the right way to analyze our intuitive thought process toward to the continuity and the maximum relations. The fact is that the real number has this some property called completeness. From there, you can conclude it always has a maximum. But again, I think this whole thing demonstrates there is a serious gap in our intuitive understanding of this maximum minimum property of a continuous function. So once you go through the proof, which is going to be the next video, carefully, you might understand the structure of real number, how that plays into the existence of this maximum for continuous functions. Thanks.